This presentation concerns the chi-squared test for the underlying distribution. The example featured here is a shifted negative exponential applied to headways. Before we begin, let's recognize that traffic engineers often observe and measure characteristics of a sample of users from a population that is effectively infinite, and that statistical analysis of the sample is used to draw conclusions about the population. Consider that I have observed a flow rate to be 810 vehicles per hour and that I have measured 100 individual headways. I know there is a reciprocal relationship between flow and average headway, so I compute average headway, h bar, as 1 over flow times 3,600 seconds per hour to give me, in this case, 4.4 seconds per vehicle. What useful information do I find within the sample of 100 observed headways taken under these flow conditions? Well, I can sort the headways from smallest to largest and find that the minimum headway in the sample of 100 is 1.363 seconds. At the bottom of the sort, not shown here, I find that the largest observed headway in the sample is 9.914 seconds. So I wonder, if I had collected, say, 500 headways or 1,000 headways, would I eventually observe a headway smaller than 1.363 seconds? Perhaps if I sample enough headways, I might eventually observe one as small as 1 second. You see, a sample is necessarily a limited view of the entire population of interest. One important question is what statistical distribution best describes the observed data mathematically? The distribution or underlying shape is often of great interest. If the population follows a known mathematical distribution, then I can use math to answer questions like, what's the probability of encountering a headway that is, say, at least 6 seconds long? So, can I use my sample of 100 headways to draw conclusions about the distribution of the population from which that sample was drawn? In a moment, I will demonstrate a test of the hypothesis that this sample of 100 headways is exponentially distributed. First, let's revisit portions of the text that have been the subject of recent study. Recall that the chi-squared test is demonstrated in Ross Chapter 7 to test the hypothesis that a sample of 100 heights is uniformly distributed. The observed sample of 100 heights appears in the second column. The hypothesis is developed in the third column in the form of a theoretical distribution. How the sample of 100 would likely appear if drawn from a uniform distribution. The chi-squared test is performed in the final column. The chi-squared test is also demonstrated in Ross Chapter 10. Here, to test the hypothesis that a sample of 283 speeds is normally distributed. In the context of a recent quiz, students demonstrated some familiarity with the statistical procedures featured here. The observed sample of 283 speeds appears in the third column. The hypothesis is developed in columns 4 through 7 in the form of a theoretical distribution constructed to discover how the sample of 283 speeds would appear if drawn from a normal distribution. Columns 4, 5, and 6 are intermediate steps towards that distribution. Those steps employ the properties of the normal distribution to compute z-values and associated probabilities. The chi-squared test is performed in columns 8 through 10. The chi-squared test is valid only where all values of the theoretical frequency are 5 or more. To achieve this in this case, columns 8 and 9 are used to combine the first two speed categories and to combine the last two speed categories in order to satisfy the greater than 5 criteria. Here, I aim to test the hypothesis that my sample of 100 headways is exponentially distributed. I begin by constructing a frequency table based on headway size. This table represents the same 100 headways shown in list form on the first. It is good practice for the analyst to formulate a statement of expectation in advance. And it'll be easier for me to formulate an expectation if I prepare an exhibit that allows me to see the shape of this sample. Here is that exhibit. I compare the revealed shape versus a convenient image of a negative exponential distribution. When I compare that shape with mine, I conclude that it's rather unlikely that my sample comes from the population that is negative exponential in distribution. Nonetheless, I'm going to do a proper test of my hypothesis. And in order to test the hypothesis of an underlying distribution that is negative exponential, I must first construct a frequency table that represents how 100 sampled headways taken under prevailing conditions would likely appear if the underlying distribution were indeed negative exponential. The prevailing condition is 810 vehicles per hour, and we have already shown that this equates to a mean headway of 4.4 seconds per vehicle. The prevailing condition is also defined by a minimum headway that we know to be 1.363 seconds. I can't know the absolute minimum headway of the population, but I'm going to assume that prevailing headways can be smaller than 1.363 and perhaps as small as 1 second. So I'm going to specify the minimum headway to be 1 second. Together, the mean headway and the minimum headway is enough information to derive a theoretical sample of 100 selected from a negative exponential distribution with a mean of 4.4 and is asymptotic to 1. Thus, the null hypothesis is the underlying distribution is negative exponential shifted 1 second. Here's how I construct the theoretical sample that corresponds to that null hypothesis. I compute the probability of a headway greater than or equal to any value t according to the function given here. This function depends on t, and I can substitute any value, t equal 1, t equal 2, t equal 3. This function depends on a, which I've defined as the minimum headway, and h bar, which I've defined as the mean headway. For example, I can determine the probability of a headway greater than or equal to 3. I substitute the corresponding values and solve for 0.555. This represents the area under the curve to the right of 3. I can do this for all values of t equal 1, t equal 2, t equal 3, and so forth, and arrange them in tabular form. See, for example, here where I have put the probability of a headway greater than or equal to 3 equal to 0.555. I use these probabilities to compute the probabilities of occurrence in each defined size category. I might be looking at a category between 1 and 2 seconds, or between 2 and 3 seconds. If, for instance, I'm looking at the probability between 2 and 3 seconds, I know that that probability is equal to the probability of a headway greater than or equal to 2 minus the probability of a headway greater than or equal to 3. We've already shown that the probability of a headway greater than or equal to 3 is equal to 0.555, and I've similarly calculated the probability of a headway greater than or equal to 2 to be 0.745. I perform the subtraction and solve for the probability of a headway between 2 and 3 seconds to be 0.19. This is the area under the curve between 2 and 3. The probabilities for each size category are organized in tabular form. Here we find the probabilities of a headway between 2 and 3 seconds to be 0.190 as previously calculated. The other probabilities for each size category are given here. Knowing the probabilities, I can compute the expected frequency if I took a sample of 100. For example, if I know the probability of a headway between 2 and 3 seconds is 0.190, I would expect in a sample of 100 to find 19 headways between 2 and 3 seconds. I can repeat the calculation for all size categories and tabulate them here. This is a good opportunity for me to confirm my sums, my probabilities summed to 1, and my frequencies summed to my sample size, 100. I have to remember that the chi-squared test is valid only when all values of the theoretical frequency are 5 or more. To achieve this, the fourth to last and third to last categories are combined. Also, the second to last and last categories are combined. We see here now that we have a category between 7 and 9 seconds that represents the two categories that existed previously, one for 7 to 8 and one for 8 to 9. Similarly, we have a category that represents all headways between 9 and 100, when previously we had a category between 9 and 10 and a separate category between 10 to 100. I compare the actual distribution from my data, the data I collected in the field, to the theoretical distribution I just constructed by using the chi-squared statistic, for which we find ample demonstration in the text. This is done for each size category, and the sum is taken at the bottom here to be 47.3. I compare the computed chi-square statistic, 47.3, to the decision value corresponding to the correct number of degrees of freedom and the analyst's choice of alpha. The degrees of freedom depend on the number of size categories, given here is 8, and the number of estimation parameters, which is 2. The two estimation parameters are the mean, which was 4.4, and the minimum, which was 1. The degrees of freedom is the number of categories minus 1 minus the number of estimation parameters. 8 minus 1 minus 2 gives us 5 degrees of freedom. I go to the chi-squared table for an alpha value of 0.05 and 5 degrees of freedom. I find a chi-squared decision value of 11.07. Given that my computed value of 47.3 is greater than 11.07, I reject the null hypothesis and conclude that the underlying distribution is not negative exponential.